Welcome everyone. In this lab I'm going to demonstrate some of the things that you need to do related to lecture 1. And I'm going to start just by introducing you a little bit to the course GitHub website and show you how to find some things there. So if you go to bios2.waldronlab.io, you'll see direct links to materials from all 10 sessions. This column called GitHub here, this will take you to a repository for each one of the sessions. And then under lecture and lab, this takes you directly to built lectures as HTML and PDF, and built labs as HTML, as well as the videos on YouTube. So just to give you a bit of background, this build passing, these badges are here because I've actually only uploaded the raw R Markdown code to each of these repositories, and then I've had the HTML and PDF built automatically from them. So if I wanted to go, let's say, to the first lab, I could click here on HTML. I see here the built version of the lab. By that I mean that all of the code has been run, there are figures in place, there are summaries of the fit in place, etc. Now, if you wanted the code, and also if you wanted to find this cholesterol.tsv dataset, you could go from here. This little cat logo is the GitHub logo to find it, or you could go, as I mentioned, from here, the git clone part. Those link to exactly the same place. But under this repository, if you click on vignettes, you will find both the source code that you can use to build your lab exercises on, and the data files. And I'll just show you that if you click on this, in order to download, you need to click on either the raw button and then save what you get, or click on this little download button, such as this. There are also options for cloning all of the data sets in one go. I have some directions for that. It's possible to download this entire repository, or if I go back to the beginning here, there are these instructions here that you could use to download all 10 sessions and all of their materials in one go. Totally optional, though. You can also do it just the way I did it. I'm just going to do this the old-fashioned way right now. Bit by bit, I'm going to click on this git clone. I'm going to click on vignettes. I've already downloaded the data set. I'm also going to download the lab file. I'm going to click on this, and then I'm going to run this. And if I were to click knit, this should just work now because I already have the libraries installed needed, and I've just now locally reproduced the production of this lab from raw code to the built object. I'm going to do some live coding here and show you going through this line by line. I'm going to use a lot of its control return on a PC or command return on a Mac to run this line by line. Now, one of the early blockers that often happens for people is just getting data into R. So I'm going to show a little trick here that makes it easier in RStudio. So once I have the data set here in my directory, under File, there's this really handy option called Import Dataset, and it has some options from text using base, from text using readr, which is a fancy package just for reading text files, and I think it also does the Excel files. And we have from Excel, from SPSS, from SAS, and from Stata. And it makes importing from all of these sources relatively easy. For text file, I like readr, A, because it happens to be really fast for large files, and B, it also helps error catching. If there's some problem in the file, a line that has been truncated and is missing some of the fields, or a 0 replaced with an O, or any of these things that can make a text file difficult to read, it can help to troubleshoot those things. So I'm going to show what happens if I open this. I'm going to click on Browse. I'm going to choose this data set that I want, cholesterol.tsv. And it shows right now what this looks like. And this is not what I want. It's getting all of these into one column. So I'm going to try instead, the default here was comma, which is not what I want. I'm going to choose, let's see, tab also doesn't quite do what I want to do, because actually this is a tricky file. It has some tabs and some spaces. So I'm just going to do white space, and that actually does what I want. So it's very handy being able to play around a little bit. And then what it does, and this is nice, is give me a bit of code preview for loading this. So I'm going to click on, I'm going to copy this text by clicking there, and then I'm going to click import. And what it has done is run this code, and then it has used the command view to pop up this little spreadsheet here showing the data that I've just imported. So we can see there that there are just 3 columns in this text file. There's a cholesterol column that seems to have all integer values. There's an age column that seems to have all integer values. And then there's a state that looks like it has values of Iowa and Nebraska. So what I could do, I forget why I had call double. This is an option in that menu that you have to actually specify the types of some of the columns. So I actually said age should be a double precision column, but that didn't work. So I'm just going to copy from down here. Remember that down there is code that is run. Up here is durable code that can go into the presentation. It's not run unless I do something like Control Enter. So this has read the code in again. And if I do, oops, I need to call this call. And there's a summary of what we have. I'm going to do one other little trick here just so that I get a better summary here. I'm going to do call state factor, call state, and now I have this nice summary of there are 11 observations from Iowa and 19 from Nebraska. And if you do your introductory R primers coming up, you'll learn what this is. This turns a character value into something called a factor, which is an alternative way of representing categorical variables in R. So we've got this data. I'm going to load the ggplot2 library. This is the topic of the first data science unit. If you follow the suggestions, it's doing some basic plots in ggplot. Here is a scatter plot where I've used 2 different colors and 2 different shapes to plot separately the observations of cholesterol versus age in Iowa and Nebraska. And we see definitely some kind of a trend in both states. They're not quite parallel, but they're pretty close. It doesn't look like the relationship is too different, although there might be some overall shift between the 2 states. These are the kinds of things that we would have to test using regression to have a better idea of. So I'm going to go ahead and do that. I'm going to fit our first regression here. It's a linear model of cholesterol as modeled by age times state. So you remember what that is? That is age and state and an interaction term between them. So I ran that linear model, and then I used summary on the resulting object fit, and it produces this summary for me. So what do we have? We have, first it tells me what the call was that produced this object. It gives me a summary of the residuals, the minimum, the maximum, the first quartile, the median, and the third quartile. And then we have a table of coefficients. And what I see is in the row called age, I see an association between age and cholesterol. And this estimate tells me that on average, for every increase of a year's age, there's an increase of 3 points in the cholesterol. This is our standard error on this estimate. And the t-value, remember I mentioned that this estimate will be t-distributed under the null hypothesis. And then finally, the probability of observing a t-value greater than or equal to this estimate, 3.2, under the null hypothesis, where the true age is 0 under a t-distribution. And we have a small p-value indicating that we should probably reject that null hypothesis of no relationship between age and cholesterol and accept an alternative hypothesis that there is some relationship. On the other hand, there is no evidence of an overall difference between the two states. Those were Iowa and Nebraska. So even though Nebraska has a somewhat higher average, this is consistent with an estimate of 0. So we're not going to reject the null hypothesis of a difference in overall mean cholesterol levels between Iowa and Nebraska. And also there's no evidence of an interaction between age and state. So if I just do ANOVA fit, it's going to produce for me that analysis of variance table for including each of the variables in the model, age, state, and the interaction with our sum of squares, mean squares, F values, and p-value for the F statistic, for the F test, for just this component of the models. So this F value is the ratio of this mean square to the residual mean square. So again, we see evidence of a relationship with age, but not for state or the interaction. Now this is not using the fancy ggplot2 package anymore. This is base package, and I'm producing what's called the diagnostic plots, or plots on the residuals. And these are a basic test to do for any regression to see if there's visual evidence of deviation from the assumptions. This par MFRO equals 2 creates a 2x2 panel that was visible on the PDF, but here just looking in line, I have thumbnails and can click between them. It's convenient for live coding. So this residuals versus fitted, this helps us to test that assumption of 0 mean of the residuals for all values of the predictors. So since we have multiple predictors, it's not convenient to look at this against all values of each predictor. So what it is instead is the fitted values. So these are the expected values of y given all of the values of x. So these are where a small y is expected, a small cholesterol value, and a high cholesterol value. And this red is a trend line fit among these, and it's showing that there's no big pattern or deviation away from 0, showing that for the people with low predicted cholesterol, the mean of the residuals is about 0, just as it is for the higher predicted cholesterol levels. If we saw something like a big parabola or some big trend, that would be evidence that there's a nonlinear relationship. This normal QQ plot is very convenient for testing the assumption of normally distributed residuals. And if the residuals are normally distributed, you will see more or less a straight line on this normal QQ plot. And that's what we see here. This is not evidence of any kind of meaningful deviation from normal residuals. And then these final two plots serve more or less the same. This serves more or less the same purpose of the first plot. The square root of standardized residuals is another look at the pattern of residuals as a function of the fitted values. There's maybe a little bit of a pattern here, but it's also partially because there aren't very many observations with the high predicted cholesterol. And then this last one, residuals versus leverage, helps to find outlier points. This Cook's distance is an estimate of the effect that an observation is having on the fit, and anything that's outside of these dashed lines here is some evidence of a very influential point. There are none here. Now, If I wanted to look at the effect of age, we did it in the previous plot, but I'm just going to do it another way here by fitting two models. And these two models are nested. We call them nested because this fit 1 contains state, fit 2 contains state plus age. So fit 1 is nested inside of fit 2. They're nested models, and when we have nested models, we can do this ANOVA. As a warning when doing this kind of nested comparison, if you have missing values, it changes everything, because if you had any missing values for age, then you will have fewer observations. Those will by default get dropped in fit 2. So you'll have different numbers of observations then between fit 1 and fit 2, and they're no longer nested models because the observation set is different. So you'll get a great big warning if that's the case. And if that's the case, then you shouldn't try to interpret the results of an ANOVA like this. But this more or less tells us the same story as before, that adding age to the model, in this case, the interpretation is it significantly reduces the sum of squares of the residuals, telling us that age is a meaningful predictor of cholesterol. All right, now in this last bit, I'm just going to demonstrate another application of regression. This is called a stepwise regression, which is used for prediction modeling using something called a Keiki's information criterion. So I'm going to start here with a fit that is our full model of age, state, and the interaction. And then I'm going to use a stepwise AIC in the backwards direction to start removing terms from the model and seeing whether the predictions become better. And this is not so much for inference or for testing hypotheses about associations between predictors and outcome. This is for prediction, and it can be used for things like propensity score modeling, which you'll learn about in your EPI class. So in this stepwise AIC, I started with, as you saw here, cholesterol as described by age, state, and the interaction. And you can see that as we removed the interaction term, the AIC went down a little bit, which is good. So it then went and looked at this just age plus state, no interaction. And we have that 28.01. As it then removed state, the AIC went up a little bit. And as it removed age, the AIC went way up. So in fact, in this case, the best model that we have is the one with age plus state. So even though state wasn't significantly associated with the outcome, it does actually make a very slight improvement on the prediction scores. So that's all for today. Thank you for watching, and give this a try. I encourage you to, but make sure that you do your data science unit. These are really good educational resources that I'm happy that you're able to just use easily, and go ahead and get credit for it. Thank you, and see you next week.